here we have a person on a planet. Obviously this is not to scale. We know that from Newton's law of gravity, every bit of the planet is attracted to every bit of the person. So each bit of the person, you can see, is being pulled by each bit of the planet. If we were to drill a hole into the Earth and this person were to go down into it, can you see that while most of the planet is still pulling downward on the person from our point of view, some of the Earth is pulling upward on this person. And so if we were to put at the feet of this person a bathroom scale up here at the top, then that person would have a certain weight. If we were to put a scale at the feet of this person down in the lower left, can you see that the person in the lower left, he would weigh less there because part of the planet is pulling him upwards. And if we moved this person to the very center of the planet, that each bit of the planet would be pulling him equally in every direction, and so he would have no weight. He would just be floating down there. Let's try a thought experiment, and let's imagine that we could drill a shaft all the way through the Earth. And of course we're going to ignore air resistance here, which would totally blow this thought experiment out of the water, but nonetheless it's fun to think about. And let's say we have a person who's running and falls into this shaft. If he starts from vertical rest, then at that location he will begin to accelerate downward through the shaft at 9.81 meters per second squared. Down he goes, and as he falls down, he's going to be speeding up, falling faster and faster and faster. Well, look where this person is right now, right about there. He is something like what we have in the lower left corner right now. And can you see that most of the Earth will still be tending to pull him downwards, but some of the Earth is tending to pull on him upwards. So while he's still going to be speeding up, he's not going to be speeding up at a rate of 9.81 meters per second anymore. He's going to be speeding up at a rate that's lower than that. And I'll just make up a number. I'll say, how about 6.5 meters per second squared? So he's still going to be falling faster and faster, but he's not going to be speeding up at 9.81 meters per second anymore. And when this person gets to the center of the Earth, part of the Earth is pulling him down, part of the Earth is pulling him up, and those two forces will be equal. So at that instant, he will have no net force. At that instant, he will not be accelerating. Now he's going to be going very fast at that point because he's been speeding up this whole time. Again, we're ignoring air resistance. So he'll have his maximum speed. As he continues to fall through the Earth, then most of the Earth is above now, and there's only a little bit below. So he's going to be traveling downward from our point of view here, but the net force on him will be upward because most of the Earth is pulling on him upward. So he's going to be slowing down. And he's going to slow down until he gets to right there, where there are two guys wondering why there's a hole in the Earth, and all of a sudden a pair of legs comes up like, hey, what's going on there? And at that instant he'll have a vertical speed of 0, at which point he'll dive right back into the shaft and oscillate back and forth just like a pendulum, back and forth. Of course, that thought experiment totally won't work on the Earth because A, we can't drill a ginormous shaft through the entire planet, and more importantly, air resistance would totally mess this thought experiment up. But it's fun to think about.